Well, in this video, I want to look at example number 7 in the Chapter 6 review worksheet we've been going over in this video series. And this one, participants in a study evaluated the accuracy of lie detectors. We're divided into two groups, with one group reading true material and the other group reading false material, and all while connected to a lie detector machine. And also both groups received electric shocks to add stress. Very fun. All right, this two-way table below indicates whether the participants were lying or telling the truth. So that'd be these two rows. And whether the lie detector indicated that they were lying or not. That would be these two columns. All right, so are the conditions met for using the normal distribution? All right, so I want to know right here, we're going to be looking at this is an example of a difference of proportions. Because we want to determine if the lie detector is accurate or not, if the person is lying. So we're looking at a difference of proportions. I'm going to open up the differential statistics formulas for means and proportions. And we go to the second page, requirements or assumptions necessary for difference in proportions. And we have formulas here, but essentially it means both samples need to have at least 10 successes and 10 failures. So I'll say requirements are met. Why are they met? Because all these categories have at least 10. So no matter what we consider to be a success or failure, whether the person's lying or not lying, the detector is saying the person's lying or not, each of these categories has 10 or more. Okay, so now we're looking at three different proportions here. Find the three sample portions. So for the proportion of time, the lie detector says the person is lying. So we're looking at only the proportion that the lie detector says the person is lying. So for we have P hat. And I'm going to say L for lying. And if we look at this value, what proportion the lie detector says that they are lying? That's going to be 31 out of 48. And if we look at P hat underscore N, this is going to be for not lying. And this is going to be, let's scroll up here, for not lying, 27 of the 48 times it says it's lying. So 27 out of 48. And for the pooled proportion, that would be pool. That would be 31 plus 27 over 48 plus 48. In that case, that would be 48 over 96. All right, now we have our sample data. We want to take conduct a hypothesis test to see if there's a difference in the proportion of times the lie detector says a person is lying, depending on whether the person is lying or telling the truth. We use a significance of 0.1, 10% significance level. So right here, we're going to use these sample data, P hat. This is the proportion that the lie detector says the person is lying if they actually are lying, 31 out of 48. And the 27 out of 48, that's the number of times, the proportion, excuse me, the lie detector says the person's lying, or the person's in fact telling the truth. All right, so I want to go through the entire process of setting up a hypothesis test. H says 0 is P sub L equals P sub N. And the alternative hypothesis would be P sub L is not equal to P sub N. I've got a underline here. Let me get rid of that. So here I've got my null and alternative hypothesis. We assume the proportions are equal, and the alternative is that they are not equal. I want to note right here that what do these variables represent? P sub L is the proportion of times. The lie detector says that a lying person is lying. Kind of strange statement. The P sub N is the proportion of times. The lie detector says that a person telling the truth is lying. So I'd say right here, this is accurate. That would be good for the lie detector test. And this right here, the second one, is we call it false positive. It says the person's lying, but in fact they're not. All right. Let me put a note really quick. Since both samples have at least 10 successes and 10 failures. Go up here, kind of notice for the first group, 31 successes, and the difference would be 17 failures. And for the group of people not lying, 27 successes and then 11 failures. So all groups have at least 10. Because that's true, we can use z-test difference of proportions. Our test statistic and p-value. For this, I'm going to go into GeoGebra. So we're going to z equals. I'm going to Google GeoGebra. Click on the probability. Click on the statistics tab. And in my pull down menu, we're going to look for z-test difference of proportions. The null is that they're equal. The alternative is not equal. We now need to type in my values here. So for the first sample, I'm going to do 31 out of 48. And the second example, we got 27 out of 48. All right, so for not equal, I get a z-score of 0.8348 or 835. 0.8348. 835 range decimals. And we have the p-value right here, and I got the not equal clip, so I don't need to double this. It's 0.4038. P-value is 0.404, rounded 3 decimals. So I've got connect the test, test statistic, p-value, and conclusion. So we we fail to reject the null hypothesis. All right, so our p-value is fairly large. It's greater than a significance level, which was given to be 10%, 0.1. So this data does not provide evidence that the proportion of times the lie detector says correctly that a person is lying differs from the proportion of times the lie detector says incorrectly. So this would not be a conclusion, say, if you were working for this lie detector company, because this evidence says that this lie detector Basically says a person's lying no matter what at about the same rate, which would be not good. Alright, and that finishes this up. I've included the assumptions and requirements. We've got the test statistic p-value and